Okay, now is the fun part. So let's take a look at how we can actually apply these algorithms to some real life problems. So for example, on what I just talked about, we have the quadratic Laplace form. So here, this is denoted as f of x. So x here is the vector x, should be bolded. Okay, so it's the x that you put in here. So if you put in the x here, meaning the values of all of these nodes, and then if we wanted to minimize this, it means that we wanted to minimize the difference between all of the nodes here, is to make sure that the sum of the different square is at its minimum. So subjected to some special restrictions, for example, we assigned this node to be 0, this node to be 1. Okay, so we have some nodes in between, and we don't know what these values are. And if we wanted to deduce this, then basically we wanted to minimize this f of x with x, some of the values in x is unknown. Okay, so let's see how we do that. All right, so here we have listed out the system of equations. So to minimize a function f, we know that that means to take the derivative and set it equal to 0. That's how you find the minimum, right? So from calculus, we know that. So here we are going to take the derivative on every single node. So here, this should be x6. So f df over dxi, and dxi means like each one of these nodes here. So from x1 to x6. For I equals to 2, 4, 5, 6. So only on the ones that you don't know what the values are, right? So these are the ones that you wanted to get, and those are the things that can make f of x different, right? So we are going to only take the derivative, let the derivative equal to 0 at these 4 points. And then we are going to assume that x1 equals to 0, x3 equals to 1, because it's given to us. By solving this whole system, you will get values, and the values are listed in blue, right? So here, x2 is 0.5, and you can expect that because from 0 to 1, what is the value that makes x1 minus x2 square and x2 minus x3 squares, the sum of this to be the minimum, is this being the average of the two, right? And here things is a little bit more difficult to see, is because like you have multiple ways to get from 0 or this x1 to x3. So here you do have to go through the actual calculations and see. But this is all doable. Okay, so you just take the derivative of f, which is x transpose times L times x, right? And then you're going to require these things. So it's basically a PDE with some boundary conditions, right? So something that we learned. So some further applications is that, so the method is very easy. You take the derivative and then you solve the Lx equal to b type problem, which is this, right? This is everything I think we learned how to do this. But the application is actually pretty powerful. We can do image processing by that. So think about this. Maybe some of the pixels here are missing. For example, this whole graph is a picture. And so let me draw it for you. For example, your picture looks like this, right? So all of the edges and nodes are listed here. So each one of these are a node with a special value. So those are the pixels, right? And then, for example, some of the things are missing here, but then you know these other values, right, on these points. Then how do you deduce that? You can use the energy efficient form, right? Like you're gonna use this quadratic Laplace form, graph Laplacian form. So then you can get some values here that makes the whole graph looks very natural, right? From this point to this point, you won't get a big gap, right? So that is one application of the graph Laplacian. You can also do optimization with this. So this is, for example, you are having a traffic flow, right? For example, this is a map, and then you have 2 points that you wanted to maybe start with X1 and then end with X3. And in the middle, there are some routes that can take you there. And what is these could be time, it could be like some, I don't know, maybe some stations that charges some values for you, but you can in the end get some numbers on this, and then you can figure out what is the most efficient way to get to from one start to the end. So you can also use that. Okay, so you're minimizing maybe the fare or maybe the time, something just suits your interest. So minimization is also a probability. And user rating recommendation, this is also, it may seem a little bit counterintuitive compared to the other two. But this one is also, you can use a certain network like this. And here, maybe each node is the rating. So you rate this, this item, maybe like 0 star, and this item is a 1 star, or maybe like from 0 to 10, maybe your scale it should be a little bigger in this sense. And then these are the related items. Maybe they don't have a rating yet, but according to how frequently these people buy these two things together, you can get some edges here, right? And maybe these edges also have weights, right? Maybe this is 6, this is 5 times these two things are purchased together, and you get this graph, right? And in the end, we are going to minimize the whole system, minimize f of x with respect to x, right? And then use the x transpose Lx, right? So you're going to minimize this, take derivative on each xi to make sure that you get a rating for each one of the items that doesn't have a rating before. And with that rating, then you can suggest your users maybe like when they buy this, and they should also consider some similar stuff that has higher rating. Okay, so maybe for example, you're going to recommend this one because it has a higher rating. Most people who buy this this item also have a really good chance of buying this one. Okay, and it has in general a better rating. So something like this, all of these uses something called network analysis, and you can actually model a lot of things using a network or a graph, right? So using nodes and edges, and the edges also may have different meanings. Like the edges have weights, and the weights have different meanings, and sometimes it's also directed, like how you are going to model, say, the Google page rank. Right, for each page, you're going from one page to another, and that is a directed graph. So all of these, when you delve into like the realm of network analysis, you will see that a lot of things can be modeled like that. And what is more important is that there is a mathematical model that would help you to interpret these graphs and maybe to get more information, just like the interpolations applications that we talked about with graph Laplacian. Okay. All right, now we're going to talk a little bit about something, another applications, just to kind of broaden your horizon about graph Laplacian.